second lesson for Unit 8 is the scalar equation of a line in when the plane is given. So again, it's a two-dimensional. We're thinking of this as a 2D or two-space problem. Again, not particularly because you don't know how to do what's on here. It's just so that in the move to 3D, a few concepts become easier to understand. So remember from yesterday, we had two equations that represent a line. It would be a point plus a parameter times a direction vector, or you can separate them into the two parametric forms where you have the x coordinate plus t times the x component of the direction vector, and then y would be the y coordinate of a known point plus t times the y component of the direction vector. That these are both good ways of representing a line in 2D, or well, 3D too, but for now 2D. All right, so the scalar equation of a line. Now you know this already. The scalar equation of a line is just, it's in the form ax plus by plus c equals 0. Okay, so it's like y equals mx plus b form, except everything's on one side, and ideally there are no fractions, right? You've kind of multiplied through until you got rid of all of them. Okay, so consider a line with the equation 4x plus 5y equals 20. Graph the line. All right, so again, the easiest way to graph a line like this is to make y 0 and solve x, then make x 0 and solve y. So when y is 0, x has to be negative 4. So negative 4, 0 has to be on this thing. And for the same argument, 0, negative 5 has to be on this thing. So, negative 4, 0 is here, 0, negative 5 is there. You draw a line that goes through those two. Okay, so I'll draw it. 4x plus 5y plus 20 equals 0. I think I must have done... Yeah, sorry. I'm sorry. I said the wrong thing. When I made x 0, right, y has to be negative 4. Yeah, and when y is 0, x has to be negative 5. Yeah, oh, I'm glad I did that. Okay, so there's the line. Now, it says determine a position vector that is perpendicular to the line. All right, so let's try this. Okay, so what I'm going to do is I'm going to draw a vector. Let's say the vector starts here. And let's measure the angle between u and u. Okay, I guess I can't do that, so let's go. I'll make a point here. So angle BAC. Okay. So I'm trying to figure out where B should go so that this becomes 90 degrees. Right? I should have thought this through more. There we go. Okay, so to make it 90, notice what's changed. Instead of going over 5 to the right and down 4, it goes over 4 to the right and up 5. So again, it took the direction vector of the original and then swapped it, right? So this vector that I just created, right? This one here is 4, 5. Now, does 4, 5 have anything to do with the equation? Right? If you look at this thing, we notice that a perpendicular vector right? The perpendicular vector is 4, 5, and it appears as though the perpendicular vector has the same, components as the coefficients in the question. Let's attempt to show this again. Let's make let's make random between I don't know, negative 5 and 5. We'll make that A. We'll make B the same thing. And we'll make C, yeah, C can just be the same. Okay, so ax plus b times y plus c equals 0. Okay, so again, you got a variety of different lines, right? Now let's graph the vector n equals ab, and then let's graph the vector point eq1, and then we'll go d plus n, vector de. Okay, so if you look here, right, this normal vector, we can also measure its angle. So can I do another point, EQ1? Does it just, yeah, so I think it just probably makes the same one. Yeah, it makes the same one. All right, so whatever, some other point over here. So angle G to B to E. Oh, it's not a B, I'm sorry. Right, so it always meets at 90 degrees. Right, every different possibility. So we come to a really important idea here. The perpendicular vector of any line in scalar form is the a coordinate, or the a coefficient, and then the b coefficient. So the components of the normal vector, by the way, just means vector perpendicular to the line, are ab, where a and b are the coefficients on x and y in standard form. Okay? Write a vector equation for the line. Okay, so a vector equation for the line, we know, needs to use either point. So let's go r vec equals either point. So negative 5, 0 is a good place to start. Plus the direction vector, so plus t. And then remember, this is the normal, so this is perpendicular to the line. If I want the line's direction vector, I swap the x and y, and then choose one of them to become the opposite sign. So I'll just choose the x to become the opposite sign, and then I'll remind myself that t is in real numbers. Another way to form the equation of a line is to use a vector that's perpendicular to the line rather than parallel. Any vector that's perpendicular to a line is called the normal vector, or more simply just the normal. And again, the normal vector also can identify a line because a normal to each line is unique. To each slope is unique. There's a specific normal for each slope. A normal is not enough to identify a line, but it is enough to identify the slope of a line. If a line is ax plus by plus c equals 0, then the normal to that line is ab. Okay, big idea right here. So the scalar or Cartesian equation of a straight line in 2-space has that form, and vector n is the normal to that line. Okay, now we could obviously work the other way around. We could start with the normal and then find the equation of the line. So it says find the equation of the line that has this normal that passes through 8, 2. Okay, so consider that a point that we know is 8, 2. We also know that the normal vector is 6, negative 10, which means you are in the form ax plus by plus c equals 0, and 6x minus 10y plus c equals 0. And we also know that 6 times 8 minus 10 times 2 plus c has to be 0. And so we get 48, take away 20 plus c equals 0. And therefore c is equal to negative. So we come up with the equation 6x minus 10y minus 28 equals 0. Again, just to quickly draw this, 6x minus 10y plus, minus 28 equals 0. So it should go through the point 8, 2, which it does. And then the normal, so let's go, can I type direction, EQ1? It comes up with the direction vector. And then I think I can type, can you do normal? No. So the normal would be 3 and negative 5, right? Or you could leave it as 6, 10. This actually does remind me something about the equation of this. Is that we should simplify it if we can, right? And you can see here everything can be divided by 2, so we can make this a little bit easier. and you can see that the normal and the direction vector would dot to make 0. So dot un gives you 0, which means they're perpendicular, right? So we know we did this right. Okay, so we found the Cartesian equation of a straight line that has that normal and passes through that point. Okay, find the scalar equation of the line defined by this vector. Okay, so again, consider that there's a point that we know. It must pass through 2, 1. Consider that the normal vector must be 5, 3, right? Swap x and y, and then make one of them negative. Since 3 was already negative, when you take the negative of that, it becomes positive, and you come up with this equation, 5x plus 3y plus c equals 0. 5 times 2 plus 3 times 1 plus c equals 0, and therefore c is equal to negative 13. So 5x plus 3y minus 13 equals 0. Quickly draw that. 5x minus plus 3y minus 13 equals 0. It does indeed pass through the point 2, 1. Its normal would be 5, 3, and its direction, the direction of EQ2 was 3, negative 5, and then we dot NV, and of course we're going to get 0. So we know we got that right. Okay, so there's the scalar equation of that line. Again, another good way to check this, another way to test your answer. Okay, so make up a t-value, get that point, then check that point. So for example, let t equal 1, then the point that I'm considering would be negative 1 comma 6, right? Because you have 2 plus 1 times negative 3 is negative 1, and then 1 plus 1 times 5 is 6. And you just check that point in the answer. 5 times negative 1 plus 3 times 6 minus 13 equals 0. Negative 5 plus 18 minus 13 equals 0. LS equals RS. So we know where that point is on the line, so we're good. Okay. Find for what value of k is this line and that line perpendicular? Well, here's an interesting argument. If two lines are perpendicular, their normals are perpendicular. Right? That's an interesting argument to think over. I mean, maybe I'll leave that one for you to think about. But anyway, they're definitely perpendicular if their normals are perpendicular. So let's make n1. The normal to the first line is 2, 5. The normal to the second line is 10 and then negative k, right? So what we know is that n1 vec dot, dot, why is it up there in the superscript? Oh, because not dot, it's bullet, right? Yeah, okay, sorry. n2 vec equals 0. Therefore, 2 times 10 plus 5 times negative k equals 0. 20 plus minus 5k equals 0. And k equals 4. So what value of k are the two lines perpendicular? Let's test my theory now. So 2x plus 5y minus 11 equals 0. 10x minus 4y plus 2 equals 0. And looks good. I don't know if I can do this. Angle EQ1, EQ2. Yeah, 270, or angle EQ2, EQ1 would be 90, right? There'd be a 90-degree angle where they meet. Okay, so there you go. K, if k is 4, the two lines are perpendicular. Really simple to do if you just remember that if the two lines are perpendicular, their normals are perpendicular. It wouldn't be too much harder to get the direction of line 1 and the direction of line 2, but it's faster if you do it the normals way. Okay, one of the major problems in this unit is how to calculate the distance from a point to a line. Now, what are they asking here, a point to a line? So imagine I had a point A, and I wanted to know what if so a good analogy for this is like if you're at point A and this is the street. So let's say you're in a park, back in a time where we could go in parks, and you want to get to this street. What would be the quickest route to get to it, right? And so like obviously you could walk over here, but that wouldn't be such a good idea. Okay, let's make well, we'll just record the distance. It's fine. So here's the distance, right, between the 2 points. A distance of 6. If I bring it closer, you can see I can shrink it down, shrink it down, shrink it down to 3 to 3.2, 3.19, and then it starts to go up again. So the distance between the two is shortest, right? It's shortest if you are traveling in a perpendicular direction. So if you notice now, if I draw the other line, if you're traveling in a perpendicular direction, you are traveling in the shortest possible path between a point and a line. So it's common to get a question like this where here there's a point Q and there's a line here L, and the question is, what is the shortest distance between Q and that line? Actually, not that easy a question to do. This is a question where you do have the skills to do this using your grades 9 through 11 work, but it's not straightforward. It would take you some time, I think, to do this. Now, the required distance here that we need to get, right? It would, you could imagine how you would do this. What would be good to get here is to project. Okay. We want to project onto N. We want to project PQ. QQ is probably just how we're feeling, not what we need. We want to project PQ onto N. Okay, and this is where those projections come back to us. If you take vector PQ and project it onto the normal, you will get the shadow that PQ casts onto the normal. And that shadow would be the length between Q and the line, and it would be perpendicular because the normal is perpendicular, and therefore it would be the shortest distance. So this idea is hugely important. Okay, again, not really so much for 2D, right? But for 3D, this is really, really valuable. So the distance that we need would be the projection of PQ onto N, and really it's just the scalar projection because we just need the length. We know the direction would be in the direction of N, right? So that doesn't matter. Okay, so here's this idea is crucial. Okay, so I'm just gonna try to draw attention to it. Okay, so let's try and demonstrate this. Okay, so here's what I'm going to do. So let's make up a question. Actually, is there a question here that we got to do? Now there's a formula here. Well, okay, I guess we can just do it. So what is the projection of PQ onto N, right? Remember how to get the projection? I'm gonna have to copy this. This is a big pain to type. The projection of PQ onto N is PQ. So PQ you dot product them, right? And then you divide by the magnitude N bec. Okay, and my never-ending battle with the formatting of this program. There we go. Okay, so this is what we need. we need to dot PQ with the normal, and then we need to divide it by the magnitude of the normal. Okay, let's demonstrate this quickly just with a quick example. So here's a line I just made up. Here's a point I just made up. Okay. Now what I'm going to do is I'm going to find the. Probably take a second to at least make the line up so I can get a normal. Okay, the normal vector would be just the I can read it right off the line there. It's 3, 8, right? It's 3 and 8. So now what I need to do is I make a vector A to C, and it's called U. And then what I want to do is dot U and N divided by the length. No, sorry, this one's divided by. I'm mixing this up now. Divided by the length of the normal. This is divided by. Okay, I get 3.36. Okay, now let's say I wanted to find where along the line that was. What I'm hypothesizing, by the way, is that if I draw a circle at point C with a length of A, it will be tangent to this line. It will reach exactly once, right? And if you zoom in here, I believe that theory is correct. Okay, so we got the right answer, although we still don't really know, like where on the line this point actually intersects, right? So what we could do there is we could take so let's make a unit vector. So let's call it unit normal equals n divided by length n. So that's how you make a unit vector, right? Now let's travel a distance. So let's go c plus a length times unit normal. Now, of course, this is going to go the wrong way. It's going to go up. So let's make it minus, c minus a. And we get this point D. Now, segment CD, okay, is perpendicular with the line. So if we do angle BDC, you get 90 degrees. And the length of that segment is 3.36. Notice, however, the projection told me that. I don't actually need to do any of this other work where I find where D is and then, find the coordinates of D or whatever. You may need to do that in a question, but I didn't need to do it in this question. All I needed to do was find this length. Now, what is fascinating about this? Okay, what is fascinating about this is, let's just get rid of some of this stuff. So let's get rid of the unit vector, the normal, and vector U. Okay. I did not need to use point A to get that answer. Let's make another point, E, somewhere along the line, and then make a vector EC, and then let's project EC onto the normal. So remember, it would be dot V, because this vector is called V, and the normal was N, and then we divided it by length N. 3.36, right? And not just 3.36, but down to the right decimal. Now look, I can put this anywhere. Absolutely anywhere on the line. And the projection will always be the same, because I'm projecting this onto the normal, and it would cast the same shadow, right? Let's just draw this one more time. So let's go n plus d, or vector that connects d to n plus d. Okay, the shadow that I'm casting, right, for this vector is the same as this, is the same as this, is the same. They're all the same shadow, right? They would all cast the same shadow on this segment, and therefore the projection technique, right, for finding the shortest distance is is just a brilliant way of doing this, right? It's not super difficult. I just think it's such a beautiful solution, right? That you can pick any point you want on the line, project it onto the normal, and you just solve the problem, right? Now, there's another way to do this, okay, where you can do the distance. You can use this formula. I'm not keen on this formula, but it's probably because I just never remember how it works. I should probably just think about it, but it has to do with like subbing in a known point into your line's equation. like where, sorry, x1 is the point off of your line. I may work on this if there's interest, but honestly, you can use it. Feel free to use this, absolutely no problem. But to me, this solution is the way you should do it. Sorry, I'm not doing this justice. It is a very clever formula as well. I don't want to spend too much time on it because I feel like this one's more important. Okay, so it says find the distance from this point to this line. Okay, so again, let's just say the point is Q, so Q is equal to 3, negative 5. Point P is any point I want that's on the other line. Okay, so let's say I want to say it's just trying to think of what would be a quasi-easy point to use here. While I think about that, we know that the normal vector is 4 and negative 5, and a point P on the line would be, see, the problem is this is an odd number. I don't see how this is ever going to work easily, so let's just say, let's say y is 0 and x is negative 2.25. Right? So that should work, because negative 2.25 times 4 is negative 11, 0, and then 11 makes 0. Okay, so I have this. So vector QP, okay, would be equal to, how do I get from Q to P? I'd have to go negative 5.25 in the x and positive 5 in the y. The answer to my question, the distance, would be equal to, I project, okay, onto vector n, no, PQ vec, and just put the P there. Okay, that's the distance I need. Okay, so all I'm going to do here is I'm going to go vec PQ dot n vec, just put brackets around this so it doesn't, divided by n vec. Okay, and that's the distance. So all I got to do is dot them together and divide by the length of the normal, divide by the magnitude of the normal. So to dot them together, negative 5.25. By the way, I know sorry. I wrote QP and then I wrote PQ because I'm taking the scalar projection. So maybe I should actually write this down. So let's get this. Sorry, I feel like when you look at this, it's going to be confusing because I suddenly changed. So I just want to give a quick explanation. Because you are doing the scalar projection, which is always a positive value, though it can be in a negative direction, but it's irrelevant for what we're doing. QP and PQ are interchangeable because their magnitudes are equal, right? So I just want to put that there so that we're not confused as to why. I don't understand this, but anyway, whatever. Okay, so anyway, 5.25, right, times 4 plus 5 times negative 5, okay, and we'll bracket all that up, and then we'll divide it by what would be the magnitude here. Will be the square root of 4 squared plus 5 squared. Oh, I need to close that bracket. Okay, and that's the value that I'm looking for. That's the distance between the point and the line. So D would be equal to, that would be negative 21, take away 25, divided by, bracket that so we don't lose it, divided by the square root of 25 and 16 makes 41. So we add these together, we get 46. So negative 46 over square root 41. That's the shortest distance. So again, let's prove this. So let's draw the line. So 4x minus 5y plus 11 is 0. Okay. Let's draw the point I'm looking for, 3, negative 5. And then let's draw a circle from point A with 49 over square roots. What did I say it was? 41. Not 49, 46. Okay, and I'm wrong. So let's take a second to think about why. Vector QP, let's see if I got that right first of all. So P was negative 2.250. Yeah, see, there's the mistake. That point actually isn't on the line. How did I do that wrong twice in one day? If y is 0, oh, 2.75. Oh, sorry. Okay, so that should have been 2.75. Okay, so let's fix it. So that should be 7.5. That should be 7.5. This should be 7.5, which means this is actually 49, I think was. Because that would be 20 plus 3. That's 48. Right, 48. Okay, so let's draw the circle with 48. Okay, and now, right, a few mistakes later, we've got the right distance. Okay, again, let's do the vector solution. Make a random point. We'll go vector C to A. Then we're going to draw the normal vector, which is 4, negative 5. And then we're going to do dot un divided by length n. Okay, and 7.49634, which should be the same number as 48 divided by square root 41. Yeah, so there we go. So approximately 7.496, let's say. Now, I want to add something here. Now, my projection, remember, I'm gonna just put a note around this. The negative in the projection means direction, not a negative value. So the length of the projection is just the positive. It is 48 divided by square root 41. Okay, and that's just to explain, like, I got a negative, and what do you do with a negative, and what does it mean? It just means a negative just tells you that it points the other way than the normal. So, like, think about it. The normal here, the point I picked, which is the point B here, I did P to Q, and then projected that, and that would cast a shadow in the opposite direction. So I guess I should have gone through this a little more carefully. I shouldn't have done QP. I should have done PQ, but whatever. Maybe I'll change it to PQ just for the notes, but it doesn't change the answer. It's just going to get rid of that. You know what? I'm not going to do that. I'm going to leave it. It's better here that I leave it with a negative so that you know what to do if you get a negative anyway. Okay? So again, it is a bit sloppy. I'm sorry, but actually it being sloppy lets me illustrate a couple points, so let's leave it the way it is. Okay, so a line in two space can be represented in many ways: vector equation, parametric equation, scalar equation, or an equation slope y-intercept form. The points that are solutions to the equation form a line. Yeah, so any of those equations work. A couple of good things to try here, and when I think there's probably an assignment too. If there is one, I'll make sure it's posted. Please post any questions.